So definition 4.22, we have an n-bit long number and we call it a sign because the most significant bit represent the sign bit. Okay? The most significant bit represent the sign bit. If it is 1, that means it's a negative number. If the sign bit is 0, it represents a positive number. For example, let's go to this pattern. Okay? I call this a view of integer, a view of sign integer numbers. Okay? It's a 4-bit 2's complement sign integer number, and it's in base 2 and base 10. Let's take a look. Here we start from 0, 1, 2, plus sign. Okay, so up to here, plus 3, plus 4, plus 5, plus 6, plus 7. How about the negative sign? Start from here to here. Minus 1, minus 2, all the way to minus 7. All the way to minus 8. Okay? So, how are they calculated? Okay? 1, 0, 0, 0. How can it be minus 8? How can it be minus 8? You know that the most significant bit is a sign bit, and it says that this is a negative number. How could it be minus 8 base 10? That's the question. Okay? How could this be minus 7 base 10? How could this be minus 6? Okay? The answer is this formula. See that? Minus 1, this side bit 1 represent minus 8. It's minus xn minus 1 times 2 to the n minus 1 plus the rest times 2 times 2 plus 0 times 2 to the 1 plus 0 times 2 to the 0. So this is 2 to the 3. 2 to the 3, which is 8. This one is minus because if it is 1, then it's minus 1 times 8. Okay? So this formula is actually this equation 4.16. Okay? So the MSB, most significant bit, and x0 is the least significant bit. Okay? You can see the pattern. The rest this is similar to unsigned, but this is different. the leftmost term is different. Okay? The rest is similar to unsigned. Alright? Now let's go back here. Let's try this one. 1 0 1 1. The first one corresponds to minus 8. 0 corresponds to 0 here. This one corresponds to plus 2. This one corresponds to plus 1. So it's basically minus 5 base 10. Okay. Question. How about this one? 1 0 1 0. This one, let me use another color. Oh, sorry, not good. Let's use the purple. Okay, minus 8 0 plus 2 plus 0. So it's basically minus 6 base 10. Any question? Equation 4.16. This is the most important equation. Okay. So, as you can see, 1 0 1 0 is minus 6. Okay. So, what if I increase the number of bits to be 5 bits, to be 6 bits, to be 8 bits, to be 32 bits? The circle is going to be bigger and bigger to represent more numbers. Okay? So I cannot draw the circle like this. I rather use the table on page number 14. As you can see, when the n equals to 5, I increase the range from minus 16 to plus 15. Okay? But for n equals 4, I have only minus 8 to plus 7. Can you see that? From minus 16 all the way to plus 15. Can you believe me? Here, 1 0 0 0. Remember, equation 4.16, it's minus 16. Okay? 4.16, that's the main equation for 2's complement integer. Okay. And you can see something like this. 1 0 0 1. 1 0 0 1, that's minus 7. Minus 7. When I add 1 here, on the left hand side, it's gonna stay the same. The value stay the same. Can you see that? 1 0 0 as well. 1 0 0. I add 1 more here. it's gonna represent minus 8 base 10. Anyway. This is the magical part of 2's complement. Magical part of 2's complement. The dude who invented this representation is a genius. Okay, he is a genius. That's why all the CPUs in the world follow this idea, follow this concept. Even C compiler, even C++, many languages, Java, follow this idea. Okay? What's so magic about this? I will explain it to you. Remember, FB represent minus 5 base 10. Remember? FB. Where's B? Where's minus 5? Here. This is B base 16, right? 1011, that's B base 16, right? Minus 5 base 10, this is B, this is 1, it's 1B. Why 1 here? Because we use this to tell you that it's a sign bit. Okay, and what if you put one more or one more here? Let's jump to page number 16. Page number 16. Focus on minus 5. Minus 5 base 10. So this is F, this is B. Hello? FB shows up again. I'm not kidding. FB in 8-bit 2's complement represent minus 5 base 10. And we call this concept sign extension. Okay? You can put B here. You put one more. You put one more, any number of ones. It doesn't matter. You're gonna represent the same base 10 number, minus 5. Okay? Now, the inventor of 2's complement gonna say, oh, I'm so glad you guys study my idea. Okay? And if you go back to the page number 15, it's 8 bits long, right? FB. You're gonna get minus 5 base 10. If you use equation 4.16 here, the rest is positive, right? Only this part is negative. Cool? You can see that the right hand side represent the positive number, but only the most significant bit represent the negative part. So if it's 1, then your negative part shows up and it represents negative number. If it is 0, everything stay the same, just like unsigned number. See that? Can you see that? If this bit is 0, the rest is positive. Cool? Okay, so this is so easy to understand the 2's complement number. Alright. And we appreciate that you recognize this invention. Okay? It has been around for 60 years already. Maybe longer than that. But nobody knows. Okay? Okay.